Thank you for giving me chance to attending at conference. And because of the lack of the time, I made everything as elementary as possible, and my note utilizes Galois category and fiber functors, and I believe they are the best way to actually formulate and understand, but I don't mention it at all. I don't mention it at all in the lecture.
Excuse me.
Yes.
May I ask you to write more strong?
More strong. Yes. You may. Of course you may, and yeah, I will try. But my guess is this blackboard is not great. But I will try my best. So my talk is about Galois group and fundamental group and the algebra. And first, I start with fundamental group as a Galois group. Now, X in this lecture always denotes some algebraic variety, which I don't define. The coefficients inside K, the field K, which is embedded, actually a subfield of complex number. And this algebraic variety should be geometrically connected and normal, and sometimes we require to be smooth, but these details are important for those very special mathematicians. But for students, I believe that this is a good algebraic variety should suffice. This may be open, not proper. And Xn is its analytification. I don't define this neither, but it is not very important. The definition is not important. Just if you are given some algebraic variety, that is something defined by polynomials over C, actually K is embedded in C, so then you can consider the set of the solution, 0 points, or the set of the solution as a complex analytic structure. So this is just X considered as a complex variety. And take one element in the analytification. In other words, if you know the language of the scheme, this is a complex valued point of this algebraic variety. But beginners don't need to worry about this. This is just some variety, and which is complex variety, and this is its point. Then, the first theme of this lecture is to construct a short exact sequence of groups which is sometimes called algebraic fundamental group. And I don't define the algebraic fundamental groups neither. However, there is an isomorphism between the absolute Galois group of K. So just a little explanation about this is that this is so-called infinite Galois group. That is, K bar is the algebraic closure of K inside this C, this complex number. And this is just the automorphism group. So field automorphism of K bar. but those which is trivial on K, trivial action on K. And there is a canonical identification, and there is a fancy definition, but I don't go into detail. But so you may consider this is the definition of this algebraic fundamental group of spec K. I don't define spec K. On the other hand, this left-hand side is almost equal to analytic or classical topological fundamental group. Here is invisible point. So this is not equal, but there is quite resemble. And this one I don't explain, but this one I assume you should know, because this is complex variety, so it has complex topology. So it's just locally it is some disk or multi-disk. But anyway, this is just usual topological group, and I assume that this is geometrically connected, and so this is connected, and then you know that this classical topological fundamental group. If you don't know, please ask someone in this evening session. So although I don't define these things, I will give an equivalent definition, which are more elementary. May I erase this one? And actually, there is a morphism from down to up. And the profinite completion of this is isomorphic to this. So to define equivalent definition to these objects, the most important thing is some field, which I will explain. So this is a subfield, but not very simple, but very intuitive thing. So first, this calligraphic mx, this x is this x. Germs of meromorphic functions. Meromorphic functions on x, not on x. Meromorphic function defined around x. So the name of germ. So germs of merom function around x. Yeah. So this meromorphic function means not algebraic sense, but this is a complex analytic sense. I made very bad analytic sense. Technology of using complex this. Well. Don't mind. So this is meromorphic function, just locally defined around x, and this is almost nothing to do with large x, because in the algebraic setting, meromorphic function on x is meromorphic everywhere. But what I say germ of meromorphic function is that this meromorphic function suffices to define only just locally around x. And restrict this to those can be right? Can be, those can be analytically continuated to whole x n, but as multi-valued function. And then restrict it to those algebraic over the meromorphic functions. So this is the meromorphic function in the algebraic sense. So x being algebraic variety, actually x has some coordinate functions. So this is the solution of polynomials, and the polynomials are given some variables, and these variables are functions on x. And this notation kx is the functions which can be represented as a rational function of these coordinate variables. So this is just so-called meromorphic function over x in the algebraic sense, but we allow the coefficients lies in k bar, not inside k. If we restrict the coefficients to k itself, then it is written in this way. This is algebraic meromorphic functions in the algebraic sense. So just for, I heard that this school is for students. I neglect established mathematicians at all, and my explanation might be very tedious, but for specialists. But for example, if the analytic variety, I don't actually distinguish these two, but so in the case of P1 minus 2 point, 0 infinity, or affine line minus 1 point, so for example, this has some element like xr, and the very important thing is t, is the usual coordinate function. So this complex number is complex t plane. So this 0 is the point where t is 0. So this t is the coordinate function on this variety. Then, for example, e to t inverse, this has very terrible singularity at t equals 0. But if I take x to be 1, say, this is just holomorphic function, so meromorphic function around x. And for example, this one, those can be analytically continuated to whole x1 is a typical example is t is nth roots. Nth roots of t is not well defined on x. However, you can analytically continue this function like so. So here is x, and then this function can be analytically continuated. If you prefer, you may consider this to exponential of this, and log has multi-value analytic continuation. But if we analytically continuate this function along this path, which I call gamma, then what occurs is that this function becomes T2 1 over n times zeta n, where zeta n is the nth roots of unity, that is, this is exponential 2 pi I over n, which lies here in the unit circle. This is not a good picture, but anyway, what I want to say is that this is a multi-valued function. It is not mono-valued on x1, but one can analytically continuate except for 0. At 0, you can never continuate this function as a holomorphic function or analytic function. And this one is algebraic over k bar x because this has minimal polynomial. If I write this z, then z obeys the function, the polynomial equation z to n minus t equals 0. Z to n minus t equals 0. And this t is inside this. This is q bar t. I didn't specify k, but k equals q. But this one is not algebraic, so it doesn't lie here. And also, some functions like say t minus 1 to 1 over n. So t minus 1's nth roots, this doesn't live in here. Because at t equal 1, there is some singularity. And this function cannot be analytically continued to 1.
For x, c minus c.
X.
This is complete case.
Don't worry.
T minus 1 to the 1 but is not in there for the concrete case x analytic equals c minus c.
Which one doesn't? E to t. This one? This one? It's okay. Can you stand up? Point it.
No, never mind.
T minus 1 to 1 over n is not in there for the concrete case x analytic equals c minus 0.
He's just saying it's a special case that applies to your example, not in general.
Yeah, you are welcome, and I have to confess that I am very bad at hearing English because I need to translate it once in Japanese. And okay, so the most important thing is the last field. This is field, and this field is the definition of mx. if you are number theorists or algebraists, then you can prove that mx is one of the maximal algebraic extension of kx. You may put k bar. Actually, they are same thing. Unramified over x. And clearly, as I indicated, analytic continuation gives this morphism from fundamental group to the Galois group of unramified functions. Why? Mx is an element of Mx is a multi-valued functions which is defined around x, but it can be analytically continuated because just by definition along any path. So starting from some Mx, an element of Mx by analytic continuation, we have action on Mx, and it preserves algebraicity, is an easy exercise, and also it trivially acts on k bar x, because the functions in k bar x are monovalued, not multivalued, monovalued functions, so it is independent of the choice of the path because it's monovalued. So we have this homomorphism. But there is a fact, important fact, which says that these are all very close. These are very, very close. That is, and these are not, these doesn't coincide, but they are very close. So for any finite index subgroup, normal, right? Normal finite index subgroup, we can consider the fixed field. This is fixed field. I don't write. This is fixed field. Then, I am just going to define this, but I need to erase this. So, the fact is the following thing. So, pi 1 x n X usual topological fundamental group is mapped to Galois group. But not so we restrict the functions to compute the monodromy. So we restrict the functions which are fixed by the action of n. Then, because it is fixed by n, n trivially acts on this. Very tautologically. So this factors through the quotient by n. And the theorem, where this injectivity is difficult, but the theorem says that this is isomorphic. And this is a consequence of Grothendieck's version of Riemann existence theorem. That implies for any given n, there are enough many functions which separates these paths. Separates means having different monodromies. So basically it says that the existence of good algebraic functions, so it is Riemann's existence theorem, and this is called Grothendieck's version of it. Then we take projective limit of both sides. Taking projective limit might be difficult for beginners, but it's still difficult even to me. But taking this projective limit is just making the attitude clear and clear, more clear and more clear. So you should decide how you act on this smaller group, a smaller field. If you decide your attitude, then in a compatible manner, you need to decide your attitude how to act on the larger field, and larger field, and larger field, so on. So it amounts to saying that selecting one element for each n, but so that they are compatible with respect to the change of n. And the collection of such systems is the definition of the projective limit. So it is nothing but deciding the attitude, hold the field mx. And because of this canonical identity, we have this is pi 1 n, but taking projective limit with respect to finite index normal subgroup. And this construction for any group is called profinite completion. This hat is a little bit different from Richard Hein used. The feeling is very similar, but the definition is rather. Anyway, this is so-called profinite completion. For any group, take all the finite index normal subgroup and take the limit in the sense which I explained. Then the resulting thing is usually larger than the original one. Sometimes smaller, sometimes zero. It's very mysterious. But anyway, this is called the profinite completion of this discrete group. And my definition, there are many ways to define algebraic fundamental groups, and my favorite, not favorite to say the truth, I don't like this definition, but I use this in the talk always, is this definition. This is the definition of pi 1 of algebraic fundamental group of x bar of x. And here, x bar means x tensored with k bar. And this is just the same algebraic variety, but the coefficients are enlarged. The coefficients are enlarged to k bar. Now we have an extension of field. So remember that this is a meromorphic function in the sense of algebraic variety with the coefficients in k, this coefficients in k bar, and this is multi-valued functions on x, algebraic over k bar x. And the fact is that everything is Galois extension. Every part is Galois. It, for example, follows from the fact that this is the maximal unramified extension of this field. But I don't give any reasoning. Just believe me that this is Galois extension. So here and here also Galois. Then the Galois theory, unfortunately infinite Galois theory, but infinite Galois theory is almost same with finite Galois theory. So if you believe the infinite Galois theory, we have a short exact sequence of, I omit A and L from Gal, G, just G. So mx over kx bar G mx over kx G k bar x over kx and they are same. However, okay, thank you. Thanks. Yeah. We have plenty time. Don't worry. So this is a short exact sequence which is obtained for any such three pairs of Galois extensions. And as I defined here, this one is this. So this is pi 1 of algebraic pi 1 of x bar x. And I don't want to go into detail, but it is not difficult to prove that there is a canonical identification with this Galois group and this Galois group. And I should say that what I deal with is just this one. X is P1 minus 3 points. So I am not forced to do any to treat any other difficult algebraic varieties. So in this case, this is just the kx is nothing but qt, where t is my favorite coordinate function, and k bar x is just q bar t. Then this is just undergraduate exercise that this Galois group is canonically isomorphic to this one. And my definition here of the algebraic fundamental group of X is this one. So now I already defined the most important short exact sequence and also the persons living there. So this fundamental group, this fundamental group, and this fundamental group. So in this approach, it's very it is rather clear that this is just the group which governs all the monodromies of functions, So you can be easily persuaded that it is very close to the usual topological fundamental group. But because we can deal with only finite things, because any algebraic thing, any algebraic function over this should have finite monodromy, because if the degree is n, then the choice of the different conjugate is only n. So we always, this is of finite nature, limit of finite things. So this becomes profinite. And in Richard Hendricks, in his talk, we study this same group, not profinite completely, this same group by letting them act on one form. That is differential equation. Monodromy with respect to differential equation is the what Dick is going to explain. And what I am going to explain is the monodromy action of this one to the algebraic functions which are unramified over the base variety. And the first example is in the case of x is p1 minus 0 infinity, not 0, 1 infinity. And x is actually any point, but I select 1. So this is a point of t equal 1. Then mx, so k bar x is q bar t. And what is mx? So as I explained, it has functions like this. But we need to think this as an element of mx because it is our construction. And what does it mean to consider this element as an element of mx? Is nothing but element of mx. So this is a jam. This is I recall this is a jam of meromorphic functions around x. And so fixing this is to fix a branch of this one. So there are n different branches of these multivalued functions, but always, from now on, always we fix the branch so that t at 1 is 1. other possible choice is some nth roots of unit. But we don't select this, but we fix this branch. So then we can consider this element as an element of as a jam of a function at 1. So there might be many more functions which can be analytically continuated on this x. However, there are many ways to prove that this is the whole thing. So I will give a proof. So because we have bar, we have this. And by Galois theory, it surjects to so take the composite. And I have no time, but this is nothing but z hat, the completion of z. This is because at each finite level, you have Galois group, which is z over n. Because of t's nth roots has conjugate, which are zeta n times t2 1 over n. So just multiplication of this type gives whole the conjugates. And by passing to the limit, this z hat is this Galois group. And we know by topology, this is z. And we know that by Grothendieck's Riemann existence theorem, if we take the completion, then this is isomorphic. So this is isomorphic, which means that this is nothing but this. Of course, there is more direct proof. But here, I want to mention that by choosing good functions, we can concretely construct this isomorphism. Isomorphism appeared here. There is one thing which I want to explain is not choosing a point, but choosing tangential point. And my guess is I can talk until 11:2. Is it right? 11:2. Okay. Yeah. That's it. Okay. From tomorrow, it is for the computational, not computational reason, it is important to consider the point which is called the tangential point. And for simplicity, I do that only for P1 minus 3 points case. So in complex picture, it is just complex plane removed by 2 points. And this is not a point, but so-called tangential base point. And geometrically, it is described like this. But in algebraic sense, this is described as follows. So completely similar to the previous case. So this is a function, jam of meromorphic functions around 0, 1, which means defined around 0 epsilon or some epsilon, where epsilon is positive real. So it is meromorphic function which is defined any small but not empty section. Small, how to say, segment. Small segment. And then we have some thing which is those which can be analytically continuated to whole x in as a multivalued function. And then M01, which is those algebraic over kx bar, k bar x is q bar t. Then one can prove that this is non-canonically isomorphic to mx. Non-canonically but isomorphic. And it is, I believe, clear that everything can be done in a similar way. So I define I will reuse this. Just put here vector. And then this is the definition of algebraic fundamental group with tangential base point. But this is necessary for the following computation. So now I stop here, and tomorrow I will explain about the Galois action. So the action of this group by taking a section and by taking a conjugate, this acts on this. So it's tomorrow's talk. So thank you for listening.